but I did prepare something for tomorrow as well. So what we'll do is we'll try to cover both things today. It shouldn't be too dramatic. So we'll look at the tutorial T9 directory as well as the topic today is going to be Vof Field. And so we'll look at the details of it, what it really means to implement that, what does it take. So we'll do that in some non-negligible amount of detail. So we'll talk about, we'll start off with kind of what we did with NES. We'll start off with a naive approach. We'll point out the limitation, and then we'll explain from that the need to do something not named. And there's going to be two main ingredients. One will be the interface with instruction, and the other one will be the geometry fluxing. And so we'll talk about those two things in some amount of details. We'll talk about, we'll go through pretty much the details of the construction of the interface, with exception with the math. We essentially won't worry too much about the detailed derivation. We'll kind of give just the answer. And then for the geometry fluxing, we'll do it in some details in one setting, and then we'll generalize rapidly. And there I'll take a few shortcuts that give you routines that take care of all these parts. And since we've done already the copy with the flow solver, the story there will be the same. We won't really need to revisit that. So we'll directly take a Vof scheme. We'll use it to play with our Advection or deformation problem. We're going to check the behavior of the method, and then we'll use it to look at the same type of fields. So yes. All right. So let's start with the topic again is volume of fluid. Here, let me remind you that we're interested in the question of the transport of an interface that's implicitly represented via a psi J, which is defined as the volume of liquid at I over J divided by the volume of cell I over J. Well, let me write volumes. So this is the quantity of interest. So obviously, volume fraction is necessarily going to be between 0 and 1. And it needs to stay that way, or else we don't know what it means. The equation for our Vof variable involving Vof fluid is just a simple material transport equation and Advection equation. You can write like this. It's also just okay, so this is what we're working with. Because inherently this psi function is a volume average of information, we need to think about the transport of that quantity from the perspective of the finite volumes. We can't, obviously there's no meaning to the idea of a pointwise volume fraction. It would just be a Heaviside. So we're going to convert this to the corresponding conservative form of the equation, which gives us a 2 psi dt plus divergence of u psi is equal to psi times divergence of the velocity. And under the assumption that we're working with an incompressible fluid velocity, then we're left with a very straightforward equation. discretize. Note that this is not 0 if the flow is compressible. Or if the flow is in general hydro density. Or if there's evaporation. So there's lots of instances that are not irrelevant where this would have to be taken into account. So we'll stick to our assumption that the assumption we've used so far is that we have a solenoidal velocity field, and now we go after finite volume discretization. The standard finite volume discretization involves integrating over the cell volume our equation, converting the divergence of our convective flux into the surface integral of those fluxes, so basically a summation of fluxes. Now the game we're playing is finite volume schemes to be implemented is to provide this phase value of psi. We can think about the standard approach. The standard finite volume scheme will go about creating a high order reconstruction of psi over a number of cells. Typically, we'll do that over close neighboring of cells. We'll create a polynomial representation, and we'll use that polynomial representation to bring our value to the face. So we end up with some sort of a polynomial basis of value. Typical FV involves creating a polynomial reconstruction of psi of x such that second order finite volume schemes, typically what you'll do is you'll match the cell center value, because the cell center value is anywhere second order estimating the cell average value. So this is a lot if you're at second order accuracy. So you would say such that psi of position x of ij is equal to your reconstructed, is equal to the cell value of psi of ij. This is your x of ij. So that's your typical approach. That's how you put together a quick scheme. That's how you put together a possible scheme. You just have a polynomial passing through the middle point with the finite volume. But this makes no sense for us. this idea of a pointwise value of volume fraction, of liquid volume fraction, is a meaningless concept. This is, we want to avoid this notion of pointwise volume fraction. So this is fine. We can deal with the real problem. We need to find a polynomial construction psi of x such that really the integral over the cell of psi of x dx is equal to our psi at cell ij. So you fit a polynomial such that its integral passes through, its integral matches with your known volume fractions. That's okay. And then you use it to obtain what's missing, which is psi of the face, which is equal to just psi taken at the location of our cell face. So that's your standard finite volume discretization. The issue is we need to, so what we're talking about here, you can see that this breaks down rapidly as soon as we look more carefully at what is our data set. Our data set, let's do a cut through an interface. And let's look at the function of position of data. So say this is my cell I minus 1. This is my cell I. And this is my cell I plus 1. Gas to liquid. Say cell I minus 1 is in the gas. If it is pure gas, then the value of my Vof field will be identically 0. And say that my cell I plus 1 is in the liquid, then the value of that cell will be identically 1. And then I have some cell that contains both liquid and gas. So my volume fraction will be some intermittent value. Okay, something like this. This is a typical expected distribution of liquid volume fractions across an interface. How do you fit a polynomial through this? This is fundamentally a problematic situation for us to deal with. Any type of fit through that representation will involve, and then we can sketch it. Any type of fit through that representation will involve ultimately something like this. So this would be your psi of x. So that's your reconstruction, your finite volume reconstruction of your function that you want to transport, while your values are really set by psi I plus 1 is equal to 1, psi I minus 1 is equal to 0, and some intermittent value psi of I is equal to 0. What is the consequence of that? The consequence of that situation is that you will estimate at the faces some sort of intermediate value somewhere between the left cell value and the right cell value. The simplest thing you could do possibly would be upward, right? If you want to avoid this type of smearing of your discontinuous profile, you could use upwinding. If you use upwinding and that cell face, you're going to look at the direction of your velocity. If your velocity is positive, you're going to transport, you're going to go form a flux using the value from the left. At that cell, the value is positive, you'll transport using the value from the right. So those are a couple of different options. Regardless of what you do, the outcome will be the following. If your initial profile of your psi of x has an exact solution that is this. So this is your exact solution. It will be avoidable for your finite volume solution to be the smeared out vertical. And this unique numerical diffusion, it is unavoidable when you're dealing with this continuous function. But now if we think about what numerical diffusion means, well, let's recast this in terms of values of the function of grid cells. If I sketch this one last time, and I say that this is my cell, say I minus 2, this is I minus 1, cell I plus 1, etc. This smooth profile here literally tells me that in that cell I might have gas only. That cell might have, so let's go over here and say that cell has liquid only. That cell has some liquid and that cell has some liquid. Suddenly, our representation is incompatible with our initial assumption that we're sharp. What we end up with in that situation is two mixed cells separating a gas from the liquid cell. The only way for this to happen is for some mixing to have happened in the interfaces, or for high-level curving to be taking place within a problem. Right? You need to have some penetration of the phases for this to happen. So as soon as we have this, we don't have a sharp interface anymore. We don't know how to work out from there where our interface should be located. Right? This says that cell contains the interface. This says that that cell contains the interface. Multiple interfaces. So the conclusion is that when we were working with the level set method, dispersion errors were a real problem that we had to avoid them, and we were okay making diffusion errors in order to guarantee some sufficient levels. That was fine. With the VRF method, this trade-off is not acceptable. Dispersion errors, the asymmetry VRF solution is not an acceptable outcome, but the diffuse outcome is not an acceptable outcome either. So we're going to need to find schemes that have effectively no dispersive behavior and no diffusion behavior as far as the interface normal direction is concerned. So we don't want things to diffuse normally to the interface, and we don't want oscillations to develop normally to the interface. So here we cannot define a sharp interface. So overall, we need schemes that are diffusion and dispersion error free in the interface normal direction. So let's look at what this could, what such a scheme could look like. Well, it's not particularly complicated to imagine a way to transport a VOF field information that does not spread the front in any way. The simplest way to get this would be to transport the front itself. If I know where my interface is, and I move my interface in brackets and compute the volume of that moved interface, then I will have not spread artificially my volume at all. So that goes for geometric treatment of the interface. So let's see how this would look like with our little problem. So if I'm looking at a flow, a 1D flow next, give myself grid cells. This is cell I-1, cell I, and say cell I+1. This is going to be gas. This is going to be liquid. If I have now the information of where the interface is located, okay, so that's a big if, and we'll have to work on that. Let's say my interface is located right here. I can now take my surrounding velocity field, so let me say that that cell I have velocity ui minus 1/2. And then that cell phase I have ui plus 1/2. Now suddenly, if I've given myself this interface, I can do anything. The simplest thing I can do is interpolate that velocity to the position of the front, and I can use that to move my front. So say that velocity is the same as this velocity, I interpolate, I get my velocity here, and I will move that front forward within my time step. And that will allow me to say that this cell, which was partially filled by the motion of this, has now become completely full. And that cell that was fully empty is now becoming partially full. In general, moving an interface is not necessarily that simple, but it's a possibility. An alternative option is to move the cell face. So I can take that cell face, or that cell face equivalently, and I can move them. For example, I can take that cell face and moving it backwards time by an amount that corresponds to my velocity, and say that everything in that volume, or in that region here, has to have moved through my cell face I plus 1/2 during my time step. Okay, this is the same, this is just the equivalence of an Lagrangian perspective. I'm not moving the interface, I'm moving instead the mesh at the velocity. And so that will equivalently tell me that a certain amount of liquid here, characterized by the interface, has been moved from the left cell to the right cell. So this purple region here, that is delta t, I guess minus delta t times u I plus 1/2. This represents the region over which my flow has moved it represents the region of the flow that moves through cell phase I plus 1/2 in my time step. This is what we're going to refer to as a flux volume. Or equivalently, this is the volume of flow, or volume of fluid, donated during delta t by cell I to cell I plus 1 through phase I plus 1. So those are simple geometric statements regarding how this interface or how the flow moves through our cells. Now, if I know exactly, so if I tell you that this entire purple region moves from cell I to cell I plus 1, then if I want to know the amount of liquid that moves from cell I to cell I plus 1, I just have to look at what is the amount of liquid that I have within that purple region. Okay, so the argument here is from geometry, provided we know the interface location, we can design a scheme that never will lead to any type of spread. We're truly displacing this interface while keeping it sharp. Does that make sense? Any questions on this? So this is a big requirement, and so let's get this out of the way. Right? The question now is, how do I get my interface location? In 1D it's easy. If I tell you that the cell is gas on the left, liquid on the right, is 50% liquid, then 40% of the way from the right of the cell as you move towards the left, the rest of the interface is done. In 2D it's already a lot more complicated. Interface reconstruction. So the main reference for this. So first, let me mention that we talked yesterday morning, or this part I remember, about simple interface calculation. Or we're using either vertical lines. We're going to go to the next step and do directly what we call piecewise linear interface calculation. So we're going to look for a general planar representation of an interface within itself. So we're going to do piecewise linear interface calculation. Click. Main reference that we're going to invoke here. So that's the main reference for the method. That's the main reference that will be useful for us to refer to it. I think it is included in your postback. It is the paper by Scaldavelli. Zaleski. Titled Analytical Relations Connecting Linear Interfaces and Volume Fractions. In rectangular grids. It is a Journal of Computational Physics paper. that's going to be our main reference for the next few minutes. So our goal now is, given a transported volume of fluid, I want to know where the interface is located so that I can then conduct this geometry transfer. So my goal at this point is to solve obtain reconstruction of interfacial geometry as in the form specifically of a line segment in 2D. That contains the interface. I'm not free anymore. So, if we have a situation like that, so first of all, we'll give ourselves some known information. We will assume that we know locally what is the phi ij of the cell. Sorry, not the phi, the psi ij of the cell. And then we will also give ourselves the orientation. I'm obviously cheating for now. We don't know the orientation. We'll have to get it from somewhere very soon. But if we assume that we know both, then we need to calculate the interface in the form of mx times x plus my times y is equal to some value alpha. Again, if I'm giving, if I'm assuming that m is known, then really the only thing I'm looking for is this alpha. Okay? So if I'm in the configuration that I sketched on the left, it is not too difficult for me to deal with the geometry of that problem. Let me also give myself a cell size equal to h, okay? So if I define that point as point E and that point as point H, then I can easily find the coordinate of point E, which will be
governed by y is equal to 0, and the fact that we belong in the plane, that means I can obtain the corresponding x as being equal to alpha over mx. Similarly, if I want to know where h is located, I just set x is equal to 0 in my plane equation, and I conclude that my y is equal to alpha over my. So, not too complicated. I've made some assumptions though, and we'll clarify that in a second. So we can solve now easily the forward problem. I have this triangle, I know the coordinate of my 3 points, I know exactly where this guy is located, where this guy is located, and this is 0. I can compute the area of that triangle, and that needs to match my, my psi. So let's do the forward problem. What is the forward problem? The forward problem is, if I give you a plane, can you give me the volume fraction? So if I give m alpha, find, so give m alpha and find psi. Well, this is just the area of my let me say this is point A of triangle AEH, and that is 1/2 alpha over mx times alpha over my. Okay, if I want now the volume fraction, I divide that by h squared, and I'm done. Okay. This is one specific case. If my volume fraction is large enough, or alternatively, if my normal has tipped in one direction or the other, this point could move along this axis, and in fact, we could intersect with that cell face instead of that cell face. We can deal with that problem easily as well, so let's sketch it. So this is still my H size. This is point A. We'll stick to H here. And now what we're going to do is we're going to introduce point B, and we'll say that point E has now moved to the other side. So this is my E, and I have now this location that I'm going to call F. So what I've computed with the previous relation is in fact now this area. This area right here. To which I've included this triangle here. Well, that's not what I want, so I'm going to need to subtract this green region here, which doesn't look very green here. So I need to subtract this darker region here. So how much of a correction is this? Say it again. AHE, yes. So we've computed this entire thing. So I need to subtract this now. Right? Okay. So to subtract this, I just need to figure out how big that is. And that's easy to figure out how big that is compared to how big that is by looking at that ratio of segment length. So I can just say that so this length here is A over mx. But so let me first write this correction. So the area of the little triangle BEF over the area of the big triangle AEH is going to be the ratio of, let's call this beta over alpha over m sub x. What is beta? Well, beta is this length here. Okay? This is just the simple ratio. Sorry, squared, right? We're working with areas. And that I can compute. This is just going to be alpha over mx minus the cell size divided by alpha over mx, all this squared, which boils down to alpha minus h m sub x over alpha squared. So that's my correction. When do I need that correction? Well, I need that correction if alpha over m sub x is larger than my cell size, i.e. alpha minus h mx is larger than 0. Okay, that takes care of that case. Obviously, the same thing can happen on the other side. This guy can move up sufficiently for us to be counting for an extra triangle. So in the very same way, we can go through the same correction for the top triangle. And those corrections are additive. They're not, they're not separate cases. We can have one or the other, both corrections being required. So I'll sketch it real quick, but the story is exactly the same. So this is A. Let's put our E point back here. We're going to put our H up here. We'll introduce D here. And this is it. So I can draw my line. My line goes from here to here. That point I'm going to call G. I need the same correction, area of DGH divided by area of AEH. It is similarly going to be equal to alpha minus H times M sub Y over alpha squared. And that's to be used if alpha over m sub y is larger than h, i.e. alpha minus h times m sub y is larger than 0. Okay, so we can collect all this and we're done with the forward problem. So the forward problem is the following. I'm not going to put if statements. Instead, I'm going to use Heaviside functions to write everything nicely and compactly. The psi that corresponds to my problem is going to be the area of my triangle of interest, which is 1/2 alpha squared over m sub x, m sub y, corrected in two ways. First, use it, come on. There we go. First, by subtracting the area of my little triangle BEF if it exists. The if it exists is a Heaviside of alpha minus h times m sub x. That's the if the little triangle to the right exists, in which case I need to subtract alpha minus m sub x h over alpha, the entire thing squared. And then I have another correction, which is if the upper triangle exists, this is a Heaviside of alpha minus h times m sub y. I need to subtract the area of my tiny top triangle. Again, those are potentially additive corrections. Both triangles can exist simultaneously. Yes?
What do you mean by Heaviside of this alpha?
Well, h of alpha minus little h m sub x is equal to 1 if alpha minus h mx is larger than 0 or is equal to 0 else. Okay, but pure Heaviside.
It is easier to code this way.
I'm sorry?
It is easier to implement this way.
So for the coding, we'll need if statements, because this is not what we want. What we want is the inverse of this expression. I wanted to have a single expression to highlight specifically the fact that now you just put an inverse on this. You just inverse this thing and you're good, you're done. Well, because we have Heavisides, it's a bit more frustrating. So for our Heavisides, for our Heavisides, what we'll need to do is differentiate between different cases. That's all we'll need to do. So let's first, before we go through the algorithmic aspect, we'll just point out the obvious, which is that I just need to invert this problem. So now, invert this expression. This is a collection of two little challenges. One is dealing with those Heavisides. So Heavisides imply that we need to do some case selection or case differentiation. The second subtlety that we need to deal with is the fact that, well, there's alpha to the square power times alpha squared. This is a pretty high order polynomial, fourth order polynomial right now for alpha. So this is a root finding problem. Okay, so let's think about the cases. How do we solve this? When does this Heaviside matter or when does it not matter? Well, it doesn't matter if alpha minus h times mx is less than 0. Alpha we don't know, but h we know and mx we know. So basically, I know what is the value of alpha that turns on this value. Okay? But let's not forget that somewhere up here, I have my plane equation. I know exactly I have the plane equation, I know the m's, and I know that my Heaviside turns on when I pass through that point. So I can, in fact, completely control what is the value of alpha when I turn on this Heaviside. And I can know this a priori from the value of phi itself. So I guess what I'm saying here is simple as this. Alpha minus h times mx being less than 0 gives us a condition that alpha, that we turn on our Heaviside when alpha is equal to h times mx. Well, if I set alpha is equal to h times mx in that expression in the first place, I'll get the corresponding value of psi. Okay? That only works if I know that this turns on before this turns on. But this is not really a problem because I can always take I can always look at the symmetric problem. I can flip x and y and solve the problem such that the orientation of this plane is always with a larger gradient in x and in y. So I'll make use of the symmetry of the problem and orient it in such a way that I know that this happens before this. So I'll basically reorient my normal such that this m is larger. Yes, larger gradient means like this. So no, less. I'm getting confused, but we'll orient our normal such that this works. So let's see exactly how this is going to work. The first case of the limit of the first case will be when alpha gets equal to this. We plug into the psi equation, and that gives us the limit value for psi. If psi is less than that, I know I don't need to worry about the Heaviside. If it's more, I need to worry about the first Heaviside. And then same thing for the second. When this happens, I plug it into my psi equation, and that gives me my limit value below which I know that my psi will have to be turned on both sides. So for this, I will assume mx less. So mx less means that the main normal variation is in y. That makes sense. So that guarantees that the limit value of psi for case 1 is less than the limit value of psi for case 2. So that gives us 3 solution processes, or 3 possible values. If my current psi, the one I know I've obtained from my solution, if this is less than psi coming from my case 1 test, then necessarily my liquid triangle does not overreach on the right face or the top face. And so my solution is obtained from that simple relation, which I can invert directly to obtain my alpha in cell ij as being the square root of 2 mx my psi of ij. Okay, so I've solved the first problem. Now, if psi case 1 and psi case 2 bracket my value of psi, then that means that my triangle that pops out on the right has to be accounted for and has to be corrected for. So in this case, my relation between psi and alpha is given by this. I have only the first Heaviside that turns on. So it's alpha minus mxh over alpha squared. So this is my relation. Well, let me just say obtain alpha sub ij by solving for it. So now we have, but this is a simple expression, or reasonably simple expression that we need to invert. So that takes us back to a root finding problem. So this is this is an alpha to the 4th power equation. There's a number of roots. We can classify them and decide which one is the correct one, and we can in fact write it analytically. And then the last case. So if I scroll back up here, our decision of sorting our normals such that mx is less than my prevents this case. This case cannot show up. So we have either that case, or the third case that's possible is a situation where both sides have a triangle. So where we have both this and this popping up. That's the only other case. So now if psi is more than psi case 2, then we have to account for both corrections simultaneously. The full expression is just a tad bit more complicated than before. It looks like this. There's the correction for the right tiny triangle, and there's the correction for the top tiny triangle. And again, from that root finding problem, solve for alpha, and the problem is done. So it is tedious, but it's analytical. That's the exciting thing. So that's 2D. The 3D story is not much different. There's just more cases. There's more ways that a plane can pop out of the side faces of a triangle, of a cube. So it's a bit more annoying, and I won't hide that it is more annoying. So we're not going to go through the full 3D problem. It's just the same thing, but for a couple more hours. Instead, what we'll do is we'll just summarize the kind of the go-to scheme that has been proposed back in 2000 by Scardovelli and Zaleski. So Scardovelli worked this out and wrote it in a pretty systematic way in a short publication in JCP. So I'll just summarize the approach, and that's ultimately what we're going to implement. Well, a 2D version of that. So the Scardovelli approach is in full 3D. So let's conclude with the Scardovelli and Zaleski procedure. So we'll make a few assumptions and then we'll lift them. First, assume that delta x is equal to delta y and is equal to h. We'll lift that next. We'll start the problem. Well, of course, I should mention we know we are given psi, mx, and my. Now, so first of all, we'll save ourselves some time. If psi is very small or very large, let's not work with this thing. It's too expensive. If psi is less than some epsilon, or psi is more than 1 minus epsilon, then we'll go out of this routine right away by setting alpha is equal to some huge value. Okay, the value for epsilon, I think what Scardovelli had was 10 to the minus 12. 10 to the minus 12. It's up to you. It depends what type of accuracy you want for your volume of fluid scheme. Clearly, there's some level of accuracy at which your code has to consider that a small value is effectively 0. Now, if you're in between, we're going to start by simplifying our problems. We're going to symmetrize everything in such a way that we're always dealing with a plane that varies the slowest in x, then a bit faster in y, and the fastest in z. Okay, so we'll order our m value. So I'll just write on the side, I'll write the 2D algorithm, only Scardovelli has the full 3D algorithm. So we're going to reorder. So reorder our space, really. But let's put it by just saying reorder m. I'll do that by setting my mx to be the minimum of mx my, and my my to be the maximum of mx my. I'm not going to stop here. I'll get one step further by saying that really I don't need to ever work with a situation where, so let me go back up here. It should be clear that I can systematically assume that that point is in the liquid. If not, if my normal is pointed in the other direction, I can just flip the problem over as well. So equivalently, so what I'm saying is I don't need to solve the full problem. I can always assume that I work with positive components of my gradient, of my normal vector. If they're not, I'll need to flip the sign of what I get in the end. That's fine. We'll need to do this. So now I know that my bottom left point is going to be wet, necessarily, and the question is, and I know that the variation is going to be, well, my plane is going to be mostly in line in X. Then I define my cases. So test the various cases. My limit psi1 is equal to m1 over 2 times 1 minus m1. And this what am I forgetting? Oh, right here, right here. One little step I forgot, you need to normalize your vector. Well, normalize it in the following way, because we're going to need to manipulate mx and my simultaneously. We'll normalize mx, or we'll replace mx by mx over mx plus my, and my by mx over mx plus my. So for convenience, I normalize my mx and my such that they sum up to 1. That's all I'm saying. This way I can easily obtain my my. Did I change notation in the mean? Yeah, I'm getting confused. Yeah, okay. We're getting there slowly, but sorry, I'm getting confused with my own notation. M1 is equal to this guy, and M2 is equal to this guy. Okay, so my M1 and M2 are just the normalized, sorted absolute values of the components of the gradients, such that I can obtain M2 right away by doing 1 minus M1. Okay. So in that context, there's one more. The entire game we're playing here is. Oh, sorry. Yeah, this is a Y. Yeah. Sorry. I've probably messed up something else, but at this point it looks correct to me. Okay, no obvious mistake. I think at this point I have everything I wanted to have. So I'll continue the solution. The test here is the following. So we're just trying to use as many simplifications as possible to limit the number of steps in our calculation. I will test not directly the volume fraction, and you'll see why in a second. I will test the quantity x and see whether it is less than my limit value of my psi case ones. Do I have a triangle popping out on the right? If the answer to that question is no, then I will find my alpha is equal to the square root of 2 m1 times 1 minus m1 times x. What is x? There's one more symmetry we haven't thought about, which is the fact that if I'm more than 50% liquid, I can just do this entire process for the gas. So really, I don't ever have to consider the two tests that we've talked about on the previous page. Either I have one triangle popping out, or the second limit is, am I more than 50% full? If I am more than 50% full, then as far as the gas is concerned, I have no triangle popping out on the side, so I might as well solve the gas instead and do 1 minus my answer. So I'll make my problem more symmetric and simpler and remove one more test because we don't like tests by saying that x is really the minimum of psi, comma 1 minus psi. This way I'm either working on the liquid or on the gas. I will always minimize the number of crossings from the faces. And so this is the first, so we wrote the first test that we needed to do. We're going to need another test if x is, if psi1 x up to 1/2. So if I'm somewhere between the limit where I have a triangle popping out on the side and being up to 50%, then I get to the other solution. The other solution, if I scroll back up, is the solution that you obtain by inverting this thing here. So that allows us to never have to worry about the even more complex thing to invert. So the only thing we need is the root of that. In 2D, it's easy to express. In 3D, it's not easy, but it's, you can write it. In 2D, that gives you this answer here. Alpha is equal to x times 1 minus m1 plus m1 over 2. The manipulations and rescalings of the normals, those don't matter. The alpha value that we get needs to be corrected certainly to account for the fact that we flip the volume fraction. We either work with the liquid or with the gas. That will flip the alpha itself. So now we correct alpha by replacing it by either alpha if psi is less than 1/2, in which case we have another thing, we solve the original problem, or by 1 minus alpha if psi is more than 1/2. Okay, so this is just compressing everything as much as we can. The last thing is that we're assuming a square mesh here. It's easy to not assume a square mesh. We just linearly transform a problem by rescaling the dimensions to a unity side. So if
that alpha is also bounded by 1? No, right?
no, it's not.
Just minus alpha, right?
Oh, what is it? Thank you. So if the cell is not of unit size, oh, yes, okay, h is equal to 1 here. If the cell, okay, so this was all done for unit size cell. I'm sorry, I keep leaving things behind. If the cell is not of unit size, we just make it of unit size. So you do that by taking your m and creating an m prime that is just m sub I times the corresponding delta x. Okay. This is a key ingredient. It's not very complicated, but it looks compact in the code. Maybe 15, 20 lines. But it's very difficult to know where this comes from if we don't do it. So this way you know exactly where everything comes from. So this takes care. So if I give you a volume fraction in normal, that will return exactly where we should put a plane in order to conserve mass exactly. There's two things that are still missing. One is the normal. How do we get our normal vector? So to do this, we will allow ourselves to look around. Look around meaning we're going to look at our neighbors. So we're going to start to look at what is the local variation in volume fraction, and this will help us obtain a reasonable answer to that question. First of all, one little observation. If we were to naively treat a volume fraction as a bad level set, you could imagine, so a level set idea would be to define our normal as the gradient of psi divided by the magnitude of the gradient of psi. The issue is that this is tricky because psi is discontinuous. So I'll describe briefly a few methods. Lee, 1995. I think we mentioned that briefly, so I'll just do a quick sketch of it. The idea is to use a direct calculation of the gradient, so essentially a discretization of this based on the following idea. If I have a volume fraction and those 9 cells, Lee proposes to use a compact stencil to estimate the gradient of psi at those cell corners. So at that location is computing an mx of I plus 1/2, j plus 1/2 is equal to 1/2 of psi I plus 1, comma j minus psi I, comma j over dx, plus the same thing with the neighboring cell, psi I plus 1, comma j plus 1 minus psi I, comma j plus 1. I don't know how readable this is. There we go. And for completeness, we can do the same thing for J. So that will give you 4 different estimates for a given cell. So that's step A. Step B, we're going to average at the cell center. So for example, mx of I comma j will be 1/4 of the sum mi plus 1/2 j plus 1/2 plus mi minus 1/2 j plus 1/2 plus mi plus 1/2 j minus 1/2 plus mi minus 1/2 j minus 1/2. So you can combine all this into a single expression that's a bit shorter. It's just, it ends up summing the neighboring values and subtracting the middle one. We're not going to go further there. And then step C would be normalize. So that works okay. I'll mention the approach of Young that has been then reused for the context of the continuum surface force model, which is a method for implementing the surface tension force. As well as the continuum surface stress. It's a bit of an easier method, well, not really easier, but it's a very straightforward method. There is also 2 steps. Step A is going to be acknowledging that differentiating using simple finite difference schemes, a discontinuous quantity is problematic. So we're going to remove the discontinuity, we're going to filter our volume fraction. So we're going to filter / smooth our psi field. Step B, we're going to use central difference. So this is what's implemented in our code today. None of those methods are considered to be really state-of-the-art. If we want to go to something that's more exciting, we would have to jump to something a bit more involved. And so I'll give you one more example of what such a method might look like. We'll talk about the so-called Elvira, or also known, there's a variant of that known as E-Elvira. Those methods solve the problem of optimally fitting our interface with a plane from the perspective of a zoomed out bigger region. So instead of looking at placing a plane in our cell like Plick does, it zooms out on the neighborhood of 3x3 cells. So imagine a supercell like this, and it tries to optimally fit a plane there. And so by trying to minimize the errors through that fitting process, so basically on the larger scale we try to find the orientation, and then we zoom in, and once we know the orientation we work with our Plick algorithm. So this is a 2-scale process that is pretty appealing as a result. So if I give myself 3 by 3 cells, the black dot here signifies that this is the cell that I'm interested in. Let's say my real interface looks like this. Okay? Now, what Elvira is going to do is it's going to find, in an optimal sense, an overall orientation for my interface. Well, that's not a good or convincing looking orientation. It's going to find an overall orientation for my interface on that scale of 3 by 3 cells, such that the error between my real interface and a single plane over my 3 by 3 cells would be minimized. So the question is, what is the optimal orientation over this 3 by 3 cell region that minimizes the mismatch in volume fraction with my neighboring cells? Okay, so let me write this in plain words. Find, whoops. Find M that minimizes the yellow area. I don't know if it's visible here. I think it is. What does it mean? This yellow area is the difference between the volume under my thick red line and my known volume fraction in those cells. So let me put it again a different way. The idea is to find the line that gives the volume fraction at ij exactly and minimizes the difference in actual volume and volume given by the line in the other 8 surrounding cells. This is not an easy problem to solve. In general, it's a minimization problem. We'll simplify it by going after a least square representation, so in a least square sense. Okay, so you know the volume fraction here, 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 here. What is the line that exactly matches the volume fraction here, such that the orientation minimizes the mismatch between volume fraction under the line in that cell and under the line in that cell? That's the question we're solving. This is the minimization problem we're going through. Okay. I want to summarize the Plick advection, and then we're done. We're almost we have almost all the tools. So this gets to be pretty good. This is totally usable. There's better methods, more modern methods as well, but they all have this is probably the most clear-cut established method out there. There's other more modern methods that have some limitations in various sense. So we will be using this. So we have the normal, we have the reconstruction. Let's talk a bit about the advection. So I was talking about how we can simply move the face and that solves the entire problem. Let's actually do this. So we'll talk about geometric flux calculation with the Plick interface. So if I know where the interface is, how do I know what is the amount of volume? Okay, so I need to make one sketch. In order to specifically look at one cell face. Okay, so this is my cell I, or let's do I minus 1 for once. This is going to be my cell I. So this is my flux location I minus 1/2. Now I know where my interface is. So now this time I'm sketching this, but actually we know how to compute this. I know now that this is my interface. So to deal with this problem in multiple dimensions, we're going to be working in a direction per direction basis. So we're going to do what's called split advection. So we're going to work in X first, then in Y, then in Z. So we're never really going to tackle the full 3D nature of the problem. So having said that, let's continue with some sketching of what's going on here. My cell height here is going to be delta y, this is going to be delta x. And I have a known velocity at the cell face. That known velocity, let's call it u. Where inherently we're doing geometric transport. We're using the fluid velocity to help us deform our local geometry of the mesh. So what we're going to be doing is going to be fundamentally upwinded in nature. And it's going to become obvious how so in a second. So if the velocity goes from left to right, we'll be looking left. So the problem we're trying to solve, we described it already. We can think of it in the context of a flux volume type of approach. What is our flux volume? It is the volume or the region of space that would have to flow through my cell face during my time step in order for my flow to indeed be going at velocity u. So this is my flux volume. That's the region of space that will be donated by cell I minus 1 to cell I. How big is this? Well, its width is directly obtainable as u times delta t. Okay? What we need to know in this is specifically the answer to the following question. How much liquid? I wanted this to be blue. Come on. Work with me, iPad. So the question we want to answer is, what is the amount of liquid under this region? That will tell me precisely what is the liquid volume that flows from cell I-1 to cell I. Therefore, it will give me my flux. Now, the interesting thing is, in this situation, we in fact know everything. There's no actual calculation required. This guy, well, I don't need this. This guy is given by mx x plus my y is equal to alpha. This is known. The position in space of that point, right? We know everything about it. This distance, for example, we know that this is going to be my delta x minus u times delta t. We know everything we care to know about the geometry of this problem. We've now defined everything. Well, if I give you a rectangle of height delta y and of width u times dt located right here, and I give you this plane, well, we've solved this problem. This is taking us back to the forward Plick calculation problem. If I give you a rectangle and a plane, and I tell you what is the amount of volume under that plane, well, you can readily compute it. We did that last time. We did that 20 minutes ago. So this you can directly solve from the forward problem. So the step is, this involves a coordinate transformation. Plus rescale. Our flux volume into a unit cell. Use our resulting transformed Plick, right? So we have this small little rectangle thing. We stretch it back into a unit cell. In the process, we equivalently stretch and deform our plane. And now we make use of our forward relation and we're done. So use transform Plick equation. And the forward solution, meaning the solution from, if I give you alpha and the normal, give me the volume fraction, to compute liquid volume fraction. And you're done. That gives you your flux. So this is a surprisingly simple exercise after you've gone through the Plick derivation. So does that make sense to everyone why this is just already a solved problem? Okay. Well, so obviously I'm saying it's done. There's every time I've said that, there's always an if, because that's what CFD is about. There's always additional complications. We're done with X transport. So we can summarize the overall strategy of split advection. Step one will be perform a Plick reconstruction. Plus obtain our M vector. Step two, flux only in our only through the X faces. 3 Plick reconstruction plus obtain M for flux only through the Y faces. So effectively, we obtain here a first alpha. This takes us, so alpha obtained as a function from our psi at time n. This takes us from psi at time n to psi star. This gives us a new alpha from psi star, and this takes us from alpha of psi star to psi n plus 1. If you're in 2D, there's a nice little thing that you can do. So this splitting is not accurate. Alternating X transport, Y transport, this is what we call a first order split. If you wanted this to be second order in time, there's a first order error incurred in time because of this. You could get back to second order accuracy in time by switching to what's called strength splitting. Strength splitting just tricks this into being more accurate by doing this, then this, and at the second iteration, the second time step, you start by this and you go there instead. So that gives you, the result is as if you had a second order coupling for full time step integration. Basically, you obtain, you're doing 2 steps of X one after the other, and then 2 steps of Y one after the other. So from the perspective of integrating over a 2 dt time step size, you've now estimated you've now staggered in time your 2 dt integration, if you will. So from that simple perspective, you've increased your effective time step size, if you will. So you've increased your error, but now your delta t squared accurate. So you can manipulate that in various ways to make it work better, but overall, this is the scheme. So in 1D, this entire exercise is just beautiful. This works beautifully well. So I give, each cell gives to its neighbor the appropriate amount of liquid. The Cfi restriction in 1D is literally CFL of 1. With a CFL of 1, you can go as far as, you can basically integrate over the entire plate of the neighboring cell. The complication becomes enormous if you go at the CFL larger than 1, because suddenly you're going to be integrating over multiple cells and you're going to have to do a plate treatment of multiple cells. If you're in 2D, the story becomes somewhat more complicated. So in 2D, CFL less than 1 required. In 2D, and I think I hinted at that one of these mornings, if you're in 2D, you can be in the following situation. I can have a situation where my flow rushes in from the sides and leaves top and bottom like this. In which case, you can imagine that I can have at maximum CFL flux volumes that are now pushing towards one another within the same cell. Oh, I messed up the direction of my arrows. Sorry. Right, in 1D, the divergence-free condition prevents my velocity field from being too crazy. But in 2D, this is divergence-free. Fluid rushing in from the side, leaving top and bottom. That means that when I go through my geometric fluxing, I'll take my cell face here and move it up, and that cell face here and move it down. if I want to avoid donating or exchanging liquid twice, once through the top face and one through the bottom face, right? I need those two volumes to never be allowed to overlap. This requires a CFL less than 0.5. So let me make a few comments here. This approach is CFL limited. The splitting is typically first order in time. You need multiple reconstructions per step. I'll point out one more little subtlety here, which is that if I have in a 2D flow like this, imagine that I have, during my X transport, a full cell into which, so imagine that I have a full cell into which I'm flowing from the left some fluid. Well, yes, in the y direction, I be emptying the cell. But at the step of the X transport, I don't have any Y transport. So in a situation like this, imagine that cell is empty, imagine that cell is full of liquid, and that cell has liquid. During that time step in X, nothing happens to this side. So let's say this is full as well. And right here, I'm going to be introducing liquid from the left, liquid from the right. Okay, liquid from both sides is going to be getting in. That means that at the end of my time step, of my X transport step, I will have over 100% liquid. So I have a full cell that gets fluxed liquid inside of it. This is due to the fact that the X component of the velocity as a standalone quantity is not a divergence-free concept. So now the question is, what do we do with this excess liquid? Well, if we want to be conservative, we would need to know what to do with it, but this is fundamentally incompatible with our Plick derivation. We cannot, there's no way we can put a plane that gives us more than 100% liquid. So you can start to see that we're going to be struggling a little bit and we'll need corrections in order to account for the fact that each of our transport steps, each of our little X, Y, and Z transport steps, they're not divergence free. They will not give us bounded transport. And that's going to be an issue. So I'll say that we need a boundedness slash conservation correction to account for sub-step or the split velocity dilatation. So even though it looks like this works, in practice you deploy that, you'll see significant mass loss. You'll see that you'll go above 1%, 100% liquid. You'll get negative values. You'll need to clip. So you're going to be facing some issues with this. Okay, that's going to take us to the simple, between air quotes, solution to all those issues. we can still stick to this idea of having a semi-Lagrangian representation of our fluxing, a purely geometric fluxing, but we're going to go unsplit. The way we're going to do the unsplit transport is by following, so this is going to be unsplit geometric transport using Plick. So this is going to be using a paper of Lushenadek and Pitch, JCP 2013, I believe. So we're not going to solve all the problems, but we're going to get ourselves something that requires less work. So that's going to be the main reference for this. And I'll refer you to a paper that I think is included, was included somewhere in your course pack, maybe for tomorrow afternoon, by Oakes and myself. JCP 2014, I believe. Both papers look at fairly similar questions. This one is probably the lowest complexity, so low complexity unsplit transport, but it is not conservative. So this entire idea of having a volume of fluid and tracking the volume of the liquid, it's all fine and good, but if you track the volume of the liquid but you don't conserve it, it defeats the purpose. This is unfortunate. That paper is conservative, so this is a higher complexity. This is still an unsplit plus conservative geometric transport. But because the complexity of this is a bit higher, we're going to leave this behind. I'll let you read that if you're interested, and we're going to look at this, concept here. So we're going to embrace fully the semi-Lagrangian nature of our problem. Lushenadek's idea is to recast this geometric transport problem as a simple remapping problem. If you're interested in the transport, and if you're interested in predicting what that cell, ij, has as a value of a volume fraction, Lushenadek's idea is the following. Why not simply, why not simply provide the velocity at the cell vertices? So we're going to interpolate, step one, interpolate velocity at cell vertices. So now we're going to have a velocity that could look like, say, this. Step two, advect the cell vertices backwards in time. So that looks like simply solving d of x of the vertex over dt is equal to minus the velocity at the vertex location. Okay, so we're going to take those vertices, move them backwards in time. For this, you can use a forward Euler is the simplest thing. You can go up to a Runge-Kudai type schemes. So this guy will be here. This guy will be here. This guy will be here. And this guy will be here. And we'll say that this is where our cell used to be at the old time. Okay, so I'm basically saying from a purely semi-Lagrangian perspective, all the fluid in that blue cell is what over my time step evolves until it becomes that cell, red cell at my time. Well, now our problem is going to be the following. What is the amount of liquid in that blue cell? Because there's simple material transport happening with my equation, with my Vof transport, the only question I need to answer is what is the liquid volume fraction in the blue cell? That quantity should be constant in the red cell at my new time. So I'll say that step 3, find the volume fraction at time n in the blue cell. And I'll write this, in fact, in blue. And the final step is set my red n+1 ij psi to be equal to that blue value. Okay? This is all simple. There's one thing that's not easy, and that's that. What is this? Well, this is looking at that object, and we're going to take that object and we're going to split it up. We're going to chop it up into little chunks. So if I zoom in, if I look at this, I'll say that this is a collection of that object plus that object plus that triangle here plus that, whatever that shape is called. Okay? This is not particularly complicated. It is tedious. This is pure raw geometrical manipulation. This is computational geometry. This is splitting shapes by other shapes. Now that I have those 1, 2, 3, 4 purple shapes, I'm now going to ask the question, what is the amount of liquid in those? Well, it is not a complicated thing to ask what is the amount of liquid in those, because remember, I know what my liquid volume fraction is, and I know what my plick looks like. So say my plick looks like this. And this is my liquid. In all my cells, I know where my liquid is, and I know specifically where the interface is. So now the problem I have to go through is take each of those little guys and see whether they split them by this plane. The fraction of them under this plane will represent liquid volume. The fraction of them above the plane will represent gas. This guy will contribute no liquid, this guy will contribute no liquid, this guy will contribute this region in liquid, and this guy will contribute this little piece of stuff. This is just pure geometry. This is a closed problem. I can do it. This is the part where I'm going to cheat. We're not going to go through the very detailed derivation of all this. I'm just going to give you the routine that does this. Okay, so those ultimately, those regions are what we care about. We sum them up. That gives us our liquid volume. We sum up the others. That gives us the sum of all this gives us a total volume. The ratio of the two gives us a blue volume fraction, this psi n, and I put it in my red value and I'm done. Yes?
They are also calculating fluxes.
Well, yes, they are also calculating fluxes. This,
Theoretically, it will come out to the same.
yeah, yeah. No, I don't disagree. Yes.
Okay, you have simplified it.
They, in the paper, that
But I have also proposed.
this is not.
This one I have proposed, Lagrange integral.
No, this, so in the paper, they propose both. They
We are
explain.
calculating fluxes in generic paper.
No, they propose both. They have both. And they talk about,
Sorry, forward, backward, they are taking, and I think summing both the volume fractions for one backward forwarding and one forward.
Yeah.
Sorry, backward advection and the forward advection.
yes.
Then summing up in order to get some sort of conservation. Because
Wow.
they are not using any repairing for volume.
No, I agree, but they explicitly mathematically establish the connection between the flux-based version of the pure full cell remap, and they in the text they make it pretty clear that they, yeah, and you know I know well Vincent Le Chenadec, and it's confirmed that yes, the results are generated using this. So yeah, they don't do the flux because it's equivalent. This is this is simpler to understand. This is cheaper to implement, and this is what Le Chenadec actually uses to generate his results, since it is equivalent. Okay, any questions on this? So that's what we're going to do. I'll provide you the routine. So we'll do this, but we've done this last week. Interpolating velocities to some point is the same stuff as we did for the Lagrangian method, for the Lagrangian particle tracking. The advection, the backward advection, is the same as we did for the Lagrangian particle tracking. So this we did already, so we'll go very quickly. This step, yeah, there's nothing quick about it, so I'll give you a set of routines that do that. We won't talk about the details of it, and then we'll just get our answer. We'll need to provide the plick, so we'll go through the plick quickly, and then that will be it. So I think now we have a working, fairly simple recipe for this entire thing. Okay, ready to, oh, well, there's one more thing, but I won't write it down because we've spent enough time already. So let me unplug myself from this, and we're gonna move to all right. Okay, so we are in T9, I think. So this is taking us back to the demo flow case. Sorry, to the Zalizak disk test case. So this notched circle is what we're going to go back to. The code has not changed in a very significant way. Demo flow, the main driver doesn't call the level set stuff anymore. It calls the Vof stuff, but let's not talk about that. The visualization, well, we don't output a G function. We output a VOF function. The story, we don't need to worry too much about that. So we're going to look at the VOF code. We'll look briefly at this extra file. So now I've added two files. There's a VOF.f90 and there's a VOF_lookup.f90. This VOF_lookup.f90. This is where all the computational geometry required to cut stuff by other things and integrate all this is done. So this is an ugly looking file that we don't even need to worry too much about. I'll just point you to the routine that does what we want. So if we look at the VOF stuff, this is what we have. It is not a simple. We have about 750 lines of code here. So this is not a particularly a trivial piece of code. This was kind of the big message. Level set is easy to implement. It takes in a couple of hours you can have a level set code put together. The performance is, not bad, but not perfect. VOF can be interesting in terms of accuracy, very interesting in terms of conservation, but the expense of implementing it is high. All right, so we have a VOF variable, we have a normal vector like before. The alpha that I have for defining my Plix surface, I write it here as a dist, as a distance to the plane within each cell that contains a Plix. So the combination of my normal vector, norm x and norm y, with this dist, meaning the alpha that we've derived, that's my Plix. Okay, I won't ever build a plane beyond just providing the value of the distance. Okay, let me go to the initialization. The initialization itself is interesting. The initialization requires knowing what is the volume of liquid under my notched circle shape in each cell. That's not an easy question. If you have an analytical representation for the object that you're trying to represent, maybe you can integrate it, maybe you can't. Well, if you have a notched circle, I don't know how to integrate this shape in general. So I don't know how to tell you what is the volume under that shape for a general cell. So the approach I'm using is a brute force alternative approach. What I do is that for each of my grid cells, I'm just going to create a little tiny mesh within my cell, a 50 by 50 cell mesh that I will place on my cell, and I will evaluate according to the level set function that we put together a couple of days ago. I will use this level set function and create a level set on my tiny 50 by 50 mesh within each cell. And then I will traverse this little 50 by 50 mesh, and if I'm on one side of the level set, if the level set is less than 0, I'll say that I'm on the gas side. If it's above 0, I'll say that I'm on the liquid side. For every one of my little tiny grid cells within my real cell, I will add the area of that cell if my level set is positive. So I'm stair-stepping the level set function for my Zalizak disk problem on the refined mesh, and I integrate the corresponding Heaviside function basically on to estimate my volume fraction within the cell. So even just defining the initial volume fraction, that's an involved step. So that's what I do here. I loop from 1 to 50 in I and j. I create this little tiny, on the fly I create this tiny mesh, and I use this to call my init Zalizak, the function that we had written before that returns simply at that location the value of the distance to the z-exact function. And if it is larger than 0, then I add the volume of my tiny cell, or the area of my tiny cell. Okay? How do I solve my equations? Well, the ingredients are fairly simple if we look at them from there. First of all, I did not go through the process of making this a pure 2D problem because it was easier and cheaper for me to copy and paste it from a 3D code. So we'll look at this as a 3D transport problem where the dimension in Z doesn't matter, essentially. So what are the steps here? The steps are that I take every one of my cell and I create the cell vertices around that cell. Okay, so that's my step 1. And then I will project those vertices backwards in time. Let's go back and see what that project routine looks like. That project routine does a 4th order Runge-Kutta. We talked about that already. I will advect my points using my local point velocity. So at the vertex, I first obtain my velocity. And then I use this to advect my point. And then I go again and again and one last time in order to get the 4th order estimate. So now the question is, what is this get velocity? Well, this is the exact same routine that we use for the particles. This get velocity is right here. This is moving around on my mesh to find the closest set of 4 points that encompass my, my current point position, and then I bilinearly interpolate my velocity to that location. I do that using the u phase velocity, and then I do that using the v phase velocity. All right, so now we're starting to bring tools together and combine them pretty quickly. So I have a velocity interpolation to any point on my domain. From that, I perform a Runge-Kutta integration that allows me to take my cell vertices, move them backwards in time. This was step 1 and then step 2 of the Le-Chenadec algorithm. Once I've got my points moved backwards in time, I will not work this deformed cell right away because it has extra. In particular, that cell could become deformed to the point where it crosses its own boundaries. So that object is a pretty messy object to think about. To simplify the representation of that object, I'm going to split it as a sum of 6 tetrahedra. So I take so in the realm of a pure 2D flow, a pure 2D mesh, I have now a square. To split a square into simplices, I will just cut it into 2 triangles. I'm doing the full 3D version of that. This guy knows what I'm talking about. So I take this, cell, I split it into simplices, because simplices are easy to deal with, they're easy to orient. This is what this tet map does for me. It basically orients my vertices and it orders them in a way that allows me to obtain a tetrahedron. And then what I do with this tetrahedron is that I assign it a sign. So my expectation is because I've just deformed my cell, it might have gone to negative volume. It might have overlapped with itself in a complex way. That means that I could have negative tetrahedra or positive tetrahedra. The details of it are not that important. I'll show more examples of that in a more dynamic way with the PowerPoint presentation tomorrow. Then what I need to know is what is the amount of volume in each of those tetrahedra. Once I know the amount of liquid volume there, I can just accumulate that, sum that over all my 6 tetrahedra, and that gives me a total amount of liquid volume. This is what this function tet to flux does. If I scroll back up, you'll see that this is in fact a recursive function. What that function does is it looks at my neighboring mesh and it first establishes all the cuts with the neighboring grid cells. I want to cut down and trim my tetrahedron such that it is contained in a single cell. So this is what that routine does. It looks at whether I have intersections with cell faces, either in Y or in X. And if I do, I then perform a cut. I take my tetrahedron and I cut it up by my cell face. The result is that I'll generate on one side 1 tetrahedron, on the other side I'll generate another 3 tetrahedra. Okay, so I'm going to be increasing the number of objects I'm dealing with, but I'm going to do that in a recursive fashion. So once I'm done cutting by this object, I get my new tetrahedron, and I'm going to use that new tetrahedron and call my function again in a recursive sense. So that object that's just been cut, I'm going to send it to be cut again. Why? Because I might be sitting on the corner of my cells. So I might need to cut by that face and then by that face as well. So I will cut until I don't find any intersection of my object with my cell faces. Once I'm in this situation, I have a single signed simplex in which I want to know the amount of liquid, and I know that this thing is sitting inside cell ij. So I have one last cut to do, and that's with my Plix surface. So once I'm done cutting with cell faces, I now switch to a new cutting algorithm that is the split cutting. This is what this guy right here is. Now I'm going to be cutting by the plane that corresponds to my plic. What is the plic plane? This is this guy here. Norm x times the position of my of the various points on my tetrahedron plus norm y times the position in y minus alpha, this distance that we've talked about. That gives me the value. That tells me if this is positive, my tetrahedron vertex is on one side of that plane. If it's negative, it's on the other side. If all my vertices of my simplex are not on the same side of the plane, then I need to cut. And this is where the cutting is done. All this is automatized again using this extra.f90 file that I'm not even going to bother. Well, I'll show it to you, but we're not going to discuss it. The only thing I need to know from that is what is the amount of volume. On the gas side, I want to know the volume of the TET. On the liquid side, I want to know the volume of the TET as well. I will keep track of the volume of the TET on the liquid side, the volume of all the TETs as well. Once I've summed all these up, I take the ratio. So this is where this is what all this code looks like. The outcome, if I scroll back down, is this simple idea. I have now my liquid volume over all my TETs and my total volume in all my TETs. This is the liquid volume in my deformed cell at the old time. This is the total volume of my deformed cell at the old time. The ratio of the two is my blue psi n volume fraction. I'll take this and set it exactly as being my new updated transported volume fraction. So I'm done with this algorithm. I add to this some clipping because I don't want to. This clipping is basically saying that if I have less than whatever, I don't know what Vof law is, but if I have less than some epsilon amount of liquid, I don't want to bother carrying that and continuing to transport that. So I'll discard anything that's just minute amounts of liquids or anything that's minute amounts of gas. I add a Neumann condition to all the sides. I compute my normal, I'll show you that. And then once I have the normal, I can update my plic, meaning I can recompute my distance to the plane. The normal is down here. What I do is I call the smoothing routine. That takes my Vof, it applies a Laplacian operator on it to smooth it out a bit, and then I do a simple centered gradient. Okay. What is that smoother? It's this thing right here. I just loop over my cells, and I replace the value that I have locally by the sum of my local values. So I just take my local Vof value, average it out over my neighboring cells, and I use that as my new value. So that's my smoothing operation. Let me go back up. This is plic. We derived it in details. So once I know the normal and I have my volume fraction, I just need the distance. For each of my grid points that are not in the wall, I'll go through everything we've talked about. I normalize with my cells. I scale with my cell size, but my cell size is the same, so this is, I could skip this. I take the absolute value of my gradient in x and in y. I normalize my gradient by that sum. If if I don't have a normal vector, or equivalently, I could say if my volume fraction is very low or very high, or close to 0 or close to 1, I just set my distance to be a huge value. And I don't worry more about it. Otherwise, I normalize my normals, and here we go. Now I need to sort my points. I'm sorry, this is done here. So I flip my normal x, y, depending on whether my x component or y component is larger or less. So that's what I do here. I flip my volume fraction value as well to guarantee that it's below 0.5. And then this is my test, the test I need to perform. This is the critical volume fraction beyond which I need to deal with that extra triangle. If I'm past this, I deal with that extra triangle. If I'm not past this, I don't deal with the extra triangle. My volume fraction is just the volume of my single triangle. This is this. Else, this is the equation we obtained by our root finding exercise. And then I need to flip things. No, this was a 1 minus alpha. Wait. This was a 1 minus alpha. If the volume fraction is larger than 0.5, I don't flip the sign of alpha. I do 1 minus alpha. Why? Because adding 1 means taking my plane, putting it on the complete other side of my cell, and then the minus alpha moves my distance on the other end. So 1 here is the cell size. So this is really an h minus alpha if you want to think about this from a non-normalized standing. So in what I wrote, I think I didn't write the full algorithm. I wrote alpha is I said we flip the sign. We don't flip the sign. We set alpha to 1 minus alpha. We deal with any stretching of the cell and all this, and that essentially wraps it up. And I have I express my distance. So that's essentially it. That's the entire story. We'll couple that with the flow solver as well, and for this, for simplicity, we're just gonna, so I haven't computed the curvature from the volume fraction. The height function itself is kind of a complex thing to put in the code as well. So I'll set my curvature to 0. We're not gonna worry about that. In order to deal with my ghost read method, I still need to be able to localize where my interface is. And to do that, I'll use the following statement. I will say that I can estimate the position of my interface by taking my volume fraction and subtracting 0.5 from it. So I say that the 0.5 isosurface of my volume fraction is not an unreasonable estimate of where my interface is going to be located. I'm going to be using that into my sharp ghost fluid methodology. Okay? Before we were using the level set is equal to 0 as an isosurface that represents the interface. Now I'm going to be using the volume fraction isosurface of 0.5 as a representation of where the interface is as far as the flow solver coupling is concerned. Just 2 more seconds before we run this. This is all the lookup tables. They're just pre-computed solutions to cutting problems. It's not complicated. But we wouldn't have had to spend another day or 2 figuring out how to set up the algorithms that are going to generate those tables for us. Why tables? Because I don't want to compute anything. There's no need to compute. Okay, let's run this thing. One of the main observations I would expect you to make here is that the solver is slower with Vof by quite an amount compared to the level set solver. The fact is that all those cutting algorithms are not cheap. We deal with thousands and thousands of little triangles that need to be cut. The other thing is the algorithm we have here is full 3D as far as the cutting is concerned, because I was too lazy to rewrite it in 2D. That means that we're dealing with, momentarily, we're dealing with a 3D problem when we deal with the cutting. This is a lot of extra work. So we can first take a look at the Vof field. This is the volume fraction. It is a sharp but bounded cell-integrated Heaviside function. So you can see that, again, it is not trivial to estimate those quantities a priori, because we're looking at the volume under a curved surface integrated over a cell. As I time integrate this, you'll notice if we look at the palette here, my range goes still from 0 to 1. The scheme is incapable of becoming unbounded, because I literally look at the ratio of a subset of my tetrahedra divided by all the tetrahedra. So this has to be bounded between 0 and 1 when I compute this. All right, so this is the outcome at the end of the rotation of my circle. If we make it dense a bit, you can see what's going on. There's some deformation, some rounding of the corners. This is not unexpected. I said that we want a scheme that is dispersion and diffusion errors free in the interface normal direction, but a scheme that's error free, that doesn't exist, so we need to make errors. But we want our errors to be in the shape of the interface, but not in the shape of the profile perpendicular to the interface. So we maintain a sharp representation, that's the good news, but we do deform the interface, that's the bad news. The scheme is fundamentally upwinded. So we expect diffusion to act on this, so we expect short corners to be rounded up, to become rounded. The other interesting thing is that we don't see a significant change in our volume here. And in fact, we shouldn't. There's no expectation why there would be a change in the volume, because the method should be conservative. It is not exactly conservative, and I pointed out that the Le Chenadec scheme is not conservative in any sense, really, but the errors are going to be small overall. So this is what a Z-exact disk looks like. It's not bad. It's in fact pretty darn good. Let's look at, wait, let us run now the deformation problem. So this is again our vertical flow. We're putting a disk, we stretch this disk into this vertical flow, and then we go back in time. This, remember, for the level set, we were saying that without reinitialization, we had a very thin tail that ended up disappearing. With reinitialization, we maintained a thicker but more rounded tail. The shape at the very end was pretty poor in any case. Now you're going to see an interesting behavior related to interfacial transport. So if I look at this problem, and I plot this guy again, so let me do this, create my cut. So I'm not going to bother showing you the velocity field. You remember Well, just look at the Vof field. Oh, why is it so ugly? Something tells me I messed up the initial conditions. So that's my circle. At time is equal to 40. Now we start seeing the main characteristic of a VOF scheme. The mass here, because we're transporting the liquid volume fraction, we're transporting the liquid area into the, and we do that in a way that's nearly conservative, we can't be losing the trailing end of our ligaments. No matter how small it gets, we need to maintain it on our mesh. However, the correct solution should be to have a ligament that's not representable on that mesh. That problem is built to examine the nature of the numerical errors. So that ligament should be a very thin thing that should not be able to be represented by our scheme on this mesh. What the VOF does is it says, well, you asked me to conserve, I'll conserve, but to conserve, I'll mess up the shape. How does it mess up the shape? Well, essentially, the Plick reconstruction becomes unstable. What's going to happen is situations where truly two interfaces should start existing within the same cell, well, they're not going to be representable anymore, and we'll have a single interface. So in a situation where we should have a thin ligament, we'll end up instead placing a net cut in that cell that will terminate a structure. And then if you combine that with the action of numerical diffusion acting mostly in the tangential direction to the interface, what we end up generating is little tiny round drops. Those little drops are just large enough for our scheme to be able to maintain them on the mesh. So if we don't want to lose mass, essentially what the scheme does is it's going to give us effectively a numerical surface tension type of result. We try to generate tiny ligaments, a thin ligament. This ligament breaks into droplets that are just about as small as can be resolved by the mesh. As a result, the mass is conserved, but we have a very severe deformation of the topology here, very, very severe. I don't think I looked at the final time, and I'm surprised by what I'm saying here. It looks worse than what I would expect. As in very worse than what I would expect. So something goes, there's something that goes awry somewhere. Right, this thing inflates like crazy here. So I don't know what's going on here. That tells me that there is a bug somewhere. So I'm not sure what happened. I have a bug. I think it's almost certain that there's a bug in this. I don't see a good explanation for. It's funny because this looks exactly like it should. So I don't know if I messed up my velocity field with this case or if the transport itself is bogus. But there's something iffy here. Okay, so we maintain the ligament, but we form droplets. Let us apply this now. So any questions on the behavior of the methods here? Except for this buggy behavior that I'm not sure I can answer. So let's move to T10. And this time we'll go back. What, diesel? So let's look at what we're doing here. In this case, I think I was going back to looking at the jet, although I don't know why I called it diesel. I think it should be the same two-phase flow that I had with the level set. Let me look at the initial condition. The initial condition is given by a liquid half circle at the entrance. So we're still going to have a little half circle of liquid on the left. I can take a look at the demo flow initialization. So the setup here is, oh, I guess I just have a straight liquid jet. Well, let's not do that. So let me go there, go to demo flow F90 and change the velocity to match what we were looking at last time. That should be quick. That should just be, well, okay, let's do this first. So we'll run a velocity 2 jet and look at how this guy behaves. I don't remember, I'm sorry, I don't remember, but let's look. It probably runs and does something of interest. My interest was in demonstrating that the method is robust and in demonstrating that upon using it to look at breakup, then you don't have, yesterday we concluded that our droplets disappear. We can't possibly track a large number of small structures because they just go poof. Mask doesn't stay on our mesh. The point here was to show that this method doesn't do that and it is amenable to looking at the breakup of a liquid. So for now we have a single straight jet of liquid, no co-flow of gas. Let's look at the behavior of this. Diesel is a big bold statement for this. This is more of a planar sheet that is mostly laminar. But it runs in 2 minutes on the laptop, so it's just very close to what we would want to do. Okay, so let's look. Oh, breakup. I must have increased the velocity or reduced the viscosity because this thing is more violent. So remember, with our level set, we had this slow-moving jet from left to right that was creating this big mushroom cap that was kind of rolling up nicely, but not much was happening. We can take a look at what's going on with our flow here. This is, you guys have this, you can take a look, but my guess is that I increase the velocity and decrease the viscosity to make it more dynamic. I'm going to create, again, a surrogate for looking at the interface. I'm going to extract the 0.5 as a surface of the Vof field. Vof goes from 0 to 1, changes rapidly, discontinuously across the interface. We're just going to visualize it using a 0.5 as a surface. I'm going to draw it in black. And like we did before, I'm going to use little spheres. Now that's big. There we go. We're going to make things a bit thicker. Perfect. Let's look at our velocity field. So the big difference, one of the reasons why things are more not as simple looking as we observed for the level set is because the level set at the tip was just losing mass very rapidly. As we were rolling up this mushroom shape, mass was just disappearing. Now instead we're going to create little drops that are going to separate. Why are they separating? Because they really would want to be part of a ligament that cannot be resolved. So the constraint of trying to track the volume fraction forces us to detach structures. Those structures are mostly going to remain. I did not, again, I made the point that this method is not strictly speaking conservative. So it should be possible for you to identify those droplets, follow them and see them disappear. It shouldn't happen nearly as fast as with the level set method, but it should still be possible. But now we end up with all this that used to be lost mass, lost liquid volume that was just not represented on a mesh anymore. Now this stays. And the fact is, when you have a flow with a bunch of droplets moving around, the flow is going to be a lot more agitated. So this is our little, this way we can say we've done a diesel jet. This is your diesel injection problem. Make it round, add turbulence at the entrance, and increase the resolution. And you're looking at a not unreasonable representation of a diesel jet problem. Let me go back to this flow with this situation with a co-flowing gas. Okay, so we're going to slow down our liquid, and we're going to introduce 2 layers of high-speed gas above and below to match what we had at the end of the day yesterday. So we can see we're tearing off droplets. You can also see that the flow solver blew up, and the reason for that I'm pretty sure is just due to the fact that we're ejecting droplets that are moving the flow around, and I think the instantaneous local CFL conditions are just not verified. So I don't think there's much of a problem here, except the fact that we probably need to reduce the time step size, which would make the code more expensive. So that might have been why I went to a diesel configuration. Let me take a quick look at this source demo flow. Let me take a quick look at viscosity and time step size. So this is 10 to minus 3, and the viscosity is 0.001. That's the problem with running cases like these that are kind of disconnected from reality. It can be difficult to know whether you're running something meaningful or realistic in any way. So 10 to minus 3, 0.01. So that problem doesn't look as nice. But you can see, at least early on, one thing is already obvious, is that our gas co-flow has been entraining and detaching liquid droplets, where our flow for the level set was looking particularly boring. We probably need, again, to just reduce the time step size. Let me try that. And we could make things a bit more viscous as well. So looking at this, I'm pretty sure that I did not, that my initial conditions, all my inflow conditions, well, my inflow conditions I don't think are symmetric. I think the gas layer is closer below than it is above. Yeah, so you can see I've messed up a few things here. I did certainly break the symmetry somewhere. Yeah, so that makes it pretty boring. All right, let's stop playing with this, except if there's any comment or question. And let's look at the last case that I had. I think this was a droplet impact problem, so some sort of a mill crown type of problem. I don't remember exactly, let's just look at it. I'll let you, again, if you're interested in any one of those problems, you can take a look more directly at the initialization and the boundary conditions for them. So I think the goal here was to just let the droplet fall under gravity, I believe. Let's see. No velocity. Okay, I guess it is an impact on the pool, not on. So it's it would be a milk round type of problem. Oh. Okay, so we see a droplet, or Pac-Man, one or the other, or a tooth maybe. Looking at this, I am at this point pretty much 100% confident that I broke the symmetry of the implementation. So it's not the initial conditions, it's not the boundary conditions, although it might be problematic there as well. But I think I have a bug in the transport somewhere. I went too fast because there's no reason why the symmetry of the flow should be broken that early on. Even here, I think it's already lost symmetry. So yeah, that tells me that I put a bug in this. So let me reopen this with the latest data and let's look at the splash. Ooh. All right. Okay, so we have here our Vof field. I guess I should probably look instead at the velocity field, which would be more interesting. And let us create an isosurface of Vof as well. Let me add again the visibility of the nodes for this. There we go. We stop this. So this is the point here. So I don't know what the density ratio is, so let me take a quick look at what it is. The density ratio is 50. This is a gravity-driven flow. We should be able to see, if we look at the pressure, for example, yeah, you can see that there's a hydrostatic pressure distribution within the liquid. The droplet accelerates down due to gravity. This is the draining of this gas film problem that we were talking about this morning. So as you get those two interfaces getting close to one another, you have to get all this gas to leave. That creates high velocities. in this case, there's so much inertia in the motion that really the pressure from the gas phase pushing back and slowing down the impact has a negligible effect. And so the level of accuracy and the number of points we have in the film at the gas film at the last moment before impact change the results essentially none. So we don't need to worry about this too much. Upon impact in this pool, we see that due to the way the interface collapsed, again, this becomes an unresolvable feature. Automatically, the topology changes in a way that is not particularly physical, in a way that is numerically driven, and we end up capturing two little bubbles of gas here. Because we've created this high-speed gas jet from this region of emptying film, we end up generating a high curvature region, essentially two jets of liquids following this high-speed gas region, and those rise up into a crater. In 3D, this would take the shape of a full cylindrical crater, at the tip of which droplets would start forming according to a local instability of the film that would make it look like a crown, hence the name milk crown. Here in 2D, we don't have that mechanism. We're just inflating that crater, and once we reach the end of our resolution, at the very tip here, for conservation purposes, we'll just generate a little series of droplets. And then the entire wall of that crater falls below resolution. We see basically a full direct breakup of this film. All right, so this runs, this is stable. If you wanted to look at higher density ratios, higher velocities, the impact would become a very tough problem. There's really large velocities created upon impact. So this is not a particularly simple problem to solve. We'll talk about some of the ingredients that would provide stability even at high density ratios, even at high velocity impacts tomorrow morning. But for now, our scheme is still capable of doing that even though it's explicit. Any questions on all this stuff? So now we have both a level set and a VOF solver, even though I think the VOF solver is a little bit wonky here. All right, if not, I think that is it as far as the tutorials are concerned. Feel free to, yeah, go ahead.
Sir, this divergence value differ by two orders. In this case and in this case. So why is there that much difference?
So the divergence, first of all, is taken as is. It is not normalized in any way. Depending, as you change the problem, the typical grid size and velocity scale and all that will tell you what is a good reference value for your divergence. So what I'm saying is the order of magnitude of the divergence prior to the pressure correction is different from one case to another. If the mesh is less, the uncorrected velocity divergence will be higher. If the velocity magnitude is higher, the uncorrelated, the uncorrected velocity divergence will be higher as well. So there's some normalization aspect here that just has to do with the mesh size and has to do with the magnitude of the velocities that are reached.
This is not dimensionalized.
No, there's no active non-dimensionalization done here. So that's part of the answer. The other part of the answer is that the difficulty of obtaining a solution for a given Poisson problem changes from one problem to the next. And so right now, the way we've constrained our problem is with some effective residual, I think, or some relative residual, as well as a maximum number of allowed iterations. I think I set it at 100 or something like this. So with 100 iterations, there's only so much that you can do. And that amount that you can do depends on the difficulty and the complexity of the Poisson problem. The previous problem had a lower density ratio. So one of the big consequences of that is that the level of discontinuity of the coefficients in the pressure Poisson equation is significantly higher for this problem with a density ratio of 50 than it was for the previous problem with a density ratio of 10. So we have effectively a stiffer or a more ill-posed Poisson problem to solve. So with 100 steps, we'll be able to bring the residual down less here than before. I'll also make a comment on at least one specific method that's very good at dealing with highly discontinuous pressure Poisson coefficients. So we'll talk about that tomorrow morning a bit. But right now, our solver is not very good. It's not well suited for, our pressure solver is not very good. It's not well suited for big, discontinuous pressure Poisson problem. So we end up with a performance that fluctuates quite a bit. Other questions?
In both the cases, using Vof and level set, the breakup is essentially because of the numerical reasons.
Yes.
So it's basically pointless to do jet breakup kind of studies using a 2D.
Yeah, using 2D, yes. So fundamentally, I think this is an important message. Don't ever study breakup in 2D. It makes no sense. One thing that we can rely on to do breakup in 3D is the Rayleigh Plateau instability. The Rayleigh Plateau instability tells us that as soon as there's this bulging and necking phenomenon happening on the ligament, there's going to be an exponentially growing process that will break it up. So as long as we get the onset of that instability on ligaments, it is not unreasonable for us to rely on the mesh to truly perform the topology change, because we know that it will happen exponentially fast once the destabilization starts. It is an oversimplification. For example, if your fluid is highly viscous, you might be able to create and maintain very, very thin neck regions. So I don't want to oversimplify things, but overall, we have at least an instability that helps us guarantee that we can't get breakup too wrong, provided we get that instability. If you go to a sheet problem, we don't have such an instability. A sheet is a very stable beast. A sheet, in fact, should, and we spoke about that this morning, it's only once my two interfaces get within about 100 angstroms that will become unstable due to molecular force, due to van der Waals interactions. I can't possibly resolve this on the CFD mesh. So that means that in general, solving sheets is going to be a tough exercise. I'll talk also a little bit about some ideas that allow us to move forward with this question, but I don't think that there exist solutions to this problem yet. At least if you're doing a marker-based representation and sustain a sheet. You could say, hey, here I have a sheet. But locally, the microscale physics governing the flow in this sheet, they're not controlled by Navier-Stokes. The scales are small enough that this is now a rarefied flow problem. So at some point, we need to input some sort of a model. The good news for us is that the amount of liquid mass within a sheet is very minuscule. So provided that the main breakup phenomenon is not back breakup, and it's mostly ligaments getting stretched and pulled and becoming unstable, you can trust fairly well, I think, three-dimensional jet breakup simulations. Now, if we go back to 2 dimensions, everything is a sheet. So there's no Rayleigh Plateau instability. There's nothing to help you. You're basically systematically going to hit the limit of mesh resolution, and breakup is going to happen only because of numerical errors. So yeah, atomization is not a process that can be studied successfully in 2D. You have to pay the full 3D price. Whether it can be studied accurately in a general sense in 3D is still a work in progress. And I'll show some results along those lines tomorrow morning. But it's not a done deal at all. But yeah, it's an important distinction. Other questions? Okay, if not, thank you very much for your time. And if someone finds the bug, let me know. I'd be interested. I'm serious, but not too hopeful. But all right. Okay, have a good evening, and I'll see you tomorrow morning.